Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be talking about section 8.2 for Math 1040, the distribution of the sample proportion. In the last section, we just finished up talking about the sample mean and how to talk about a sampling distribution for that specific statistic. However, we could also do the same thing for a sampling proportion by calculating p sub hat, which is just however often it happens over the total amount of trials that you have. So how likely something is. For example, if I wanted to look at, say, if I take a group of 30 bowlers, how many of them are men? Something like that. What proportion of them are men? I could do that a lot, and I could take another group of 30 bowlers and find what proportion of them are men, another group of 30 bowlers, find another and what proportion of them are men, and I can keep doing that. And I want to be able to create a sampling distribution on p hat, or what we call the proportion itself, to find what the what the sample or the population proportion might be. So we can make another sampling distribution for sample proportions as well. However, there's going to be a few things that are going to change. Firstly, the shape of it. We still want it to be normal, but we have two different conditions to check for. We want it to be, if it's normal, we want the sample size times proportion to be, and 1 minus proportion to be greater than or equal to 10. Notice that these proportions just say p, it's not p hat, so not the actual sample proportions we get, just the overall proportion. If I multiply those together, it should be greater than or equal to 10. This condition is basically saying that I want my sample size to be big enough so that whatever I'm looking for can happen. For example, if there's something that has maybe a 3% chance of happening, and I only have, say, 10 or 12 individuals, it's more likely that it's just not going to happen with just those 10 or 12 individuals. I probably want to have a big enough sample size so I have instances of that situation both happening and not happening. So that's what this condition is saying. My sample size is big enough. However, it's a little bit different than central limit theorem. It takes a little bit more calculation. So that's my sample size big enough. I also want the sample size n to be less than 5% of the population. Or the sample size n is less than 0.05 of capital N. Now, what this condition is for is what we call the independent criterion, or the independent condition. This is saying that my samples are independent of the population itself. Theoretically, if I were to take anybody from a population, like if I were to take your friend out of the population, then the likelihood that they were selected was 1 out of however many millions of people are in the United States. Then the likelihood that you were selected would be 1 over the population of the United States minus 1. The population would technically be influenced, which means that the probabilities are dependent on each other. However, if my sample size is so small compared to the population, then that minute change is going to be mostly irrelevant. Like with the population of the United States and you and your friend. That does change the probabilities, but very, very slightly, so that's not exactly relevant. There's two ways to address this. We're either going to address it with a statement and a sentence saying that it is likely that the sample is less than 5% of the population. Or you can also calculate this right here, move over 0.05 by dividing it, and say that n divided by 0.05 is less than or equal to capital N. If we calculate what little n, my sample size, over 0.05 is, I should be able to say that that number is less than what the population is. So there's a couple different ways to calculate that, and I'll address that when an example comes up for it. The mean of the sampling proportion. If you recall, the mean from the sampling distribution for sample means was just the original population mean. Likewise here, we'll just say the mean for the sampling distribution for proportions is just the proportion itself. The standard deviation, though, yet again, is the more complicated one. And this one's going to be p times 1 minus p divided by n. All of that under a square root. So that would be the square root, parentheses, all of that stuff, in parentheses. All that stuff needs to be inside of the square root. All right, so we got to be careful with that. Couple things because of those formulas. The center, as n gets bigger and bigger, the center is still just going to be p. That's not going to change at all. Because if you look at the formula for mu sub p hat, which we say is the mean for the sampling distribution of p hat, it's just p. It doesn't depend on n. There's no multiplication of n, there's no division of n, no nothing. However, the spread, the standard deviation here, is influenced by little n. And the bigger n gets, the larger the number I divide by. And if I divide by a larger and larger number, what that means is that the overall value gets smaller and smaller. You could think of like 1/2, and then 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10. As I'm increasing that denominator, the value itself is actually getting smaller and smaller. So as n gets repeated over and over, as you have a really large n, this standard deviation should approach 0. Which means that's my distribution that I'll create. As I increase n more and more, this distribution should become more and more squished towards that center value. Which means it'll be better to find what that estimated population proportion is. Alright, so those are a couple notes about sampling proportions. Now for some, one more note and then an example. If you want to do this by hand, recall that you can always do z-scores and use that table 5 to find the probability of something. And you can still do that here. However, the formula for it is a lot nastier, or at least it looks nastier. The value that you're checking is the proportion, and you take that away from the mean of the sampling proportion, and you divide by the standard deviation of the sampling proportion. It looks basically nastier just because there's some subscripts there, but overall is the same formula as z-scores. So you can do that if you so please. Okay. So we're going to do an example here on the bottom of page 5 that stretches into page 6. According to the Congressional Research Service, 64.9% of Utah is federal land, so land that's owned by the federal government. 100 locations in Utah will be randomly selected and checked to see whether they are federally owned. Alright, so the first two, just take a little bit of calculation. The second one, shape, will take a little bit of argument. Alright, so the center. The center, we have the percentage, that's just going to be my center, 0.649. So that's my center, that's my estimated proportion. Now my spread is going to get influenced by that size of the sample, that 100. So my spread is going to be the square root of 0.649 times 1 minus 0.649, then divided by my sample size of 100. That's going to be the calculation for the spread. So if I go over to my calculator and try to type that in, I want to type in the square root of 0.649 times 1 minus 0.649 divided by 100. That should give me my standard error here, 0.0477. 0.0477. Okay. Now what we also need to do is talk about the shape, because if we can't confirm that it's normal, then we can't really do normal distributions on this. Our first condition for the shape is to check NP 1 minus P. Our sample size is 100. So that means we're going to do 100 times P, which is 0.649. So 0.649 times 1 minus 0.649. We want to confirm if that is greater than or equal to 10. So that's what we're going to do over here. So let's do 100 times 0.649 times 1 minus 0.649. If I plug all that in, what I get is 22.78. Now, it doesn't exactly matter what it is, like how big the exact number is. So I'll just round to arbitrarily 22 or 23, doesn't really matter. All that matters is that it's bigger than 10. As long as it's big enough, then we're good. That's one condition. We also need to check our second condition. So I'll say this is condition 1. For a second condition, we also need to check if our sample is small enough compared to the population. So the first condition is if the sample is big enough, but we also need it to be small enough. So kind of like a tightrope act here. To do that, we can either make a statement arguing that 100 locations, that 100 locations is less than 5% of all locations. So 100 locations is likely less than 5% of all locations. Something like that. Or what we could do instead is just argue it mathematically by doing our sample size 100 dividing by 0.05. So if I do 100 divided by 0.05, what we get is 2,000. And trying to argue that that is less than or equal to the population size. Now, we don't really know what they mean by locations. Like, I don't know if they mean like a location as in just like a spot on the ground in like a 1 foot square space or something, or if they mean like a city size location. Not exactly sure. I'm not exactly sure. So we could probably just kind of handwave this away a little bit and say it's likely that 100 locations is less than 5%, or that there's more than 2,000 locations in Utah, something like that. Again, I would want to know more about what they specifically mean by locations, but yeah. All right. So this is probably okay. With that said, we should be able to confirm and move on with this using our mean and standard deviation. So remember, our mean is 0.649, our standard deviation is 0.0477. So our mean is 0.649, and our standard deviation is 0.0477. All right, what is the probability that in a random sample of 100 locations, no more than 60% will be owned by the federal government? So no more than 60%. Now, that percentage may throw some people off, because some people will see that percentage and say, oh, okay, we have the area, and we're trying to find the bound. However, keep in mind that we're working with sampling proportions, which means that the x-axis itself are representing proportions as well. So that 60%, which is how much is owned by the federal government, that's a value on the x-axis. And that 60% would be somewhere below 64.9. So I'm going to say 60% is somewhere down here, and we're trying to find no more than that. So we're trying to find the area up to 60%. Now, we've already confirmed that this is normal, so we should be able to run normal CDF on this and try to find our area. So we have negative infinity up to 0.60, followed by our mean of 0.649, and our standard deviation of 0.0477. So we should be able to run normal CDF on that in our calculator. Lower bound, so negative infinity, so a bunch of 9s, 0.6, 0.649, and 0.0477. What we get is a probability of about 15.21%. So there's if they were to take if they were to do this 100 times, or they took 100 locations, we'd expect about 15 of those situations to result in no more than 60% being owned by the federal government. So that's our percentage chance of this happening, of having 60% or 0.6 of those locations to be owned by the federal government. All right. Now the second one is very, very similar. However, they just structure it a little bit differently. What is the probability that more than 72 locations in the sample are federal land? So we're still working with the sample, and it says 72. Unfortunately, what we have to be careful of is that we don't just use 72 directly. What that 72 really is 72 out of the 100 locations, or as a proportion, 0.72 of those locations. That's what we're going to graph, and that's what we're going to analyze. So with 0.649 still in the middle, we have 0.72 is somewhere above that, and we're trying to find that more than 72, so the area above. For sake of brevity, I'm going to, from now on, just say normal CDF. I'll just do NCDF. And we have 0.72 up to infinity, followed by 0.649 and 0.0477. So run this yet again. Those last two values should still be in there, so 0.72 followed by infinity, and we still should have our mean and standard deviation as we did before. We get approximately, in this case, 6.83%. All right. A couple more on this example. Would it be unusual to randomly sample 100 locations and find 72 or more percent of them are federal land? Well, based on our answer here, we have that 6.83%. That is greater than 5%. So, no, this would not be unusual because this is too large. What if the random sample only had n equals 30? Is this enough to say the distribution of the sample proportion is approximately normal? All right. Well, before we've been working with the sampling distribution of 100 and everything was okay. However, that's because we had already confirmed that it was normally distributed. Now we have a different sample size, so we have to be careful. The second condition is probably still okay. That second condition in this case being 30 divided by 0.05. If I do 30 divided by 0.05, 30 divided by 0.05, I should get 600. And if we said earlier that 2,000 was less than all locations in Utah, or less than 5% of all locations, if there's more locations than 2,000 in Utah, then there's also more than 600, so that should be okay. But that first condition is kind of the problem, where we have to check NP 1 minus P, and we want to make sure that's greater than or equal to 10. Well, if I run this now with 30 instead of 100 times 0.649 times 1 minus 0.649, I want to confirm if that is still greater than or equal to 10. So let's see. If I go over here, do 30 times 0.649 times 1 minus 0.649, what we get is 6.83. Approximately. Doesn't really matter. That value, unfortunately, does not follow this condition. This is not greater than or equal to 10. So, no. We cannot claim that it's approximately normal. In order to find how many more would need to be sampled, we can run through NP1 minus P greater than or equal to 10 and instead solve for n. So I'll do that over on this side here. I'll erase what we had written down, and I'll redo this and solve for what n would need to be. So we know that 100 works. We know that 30 doesn't. So we're looking for a number in between there. So if I have NP1 minus P NP1 minus P, and that's greater than or equal to 10. If I want to solve for n, what I can do is divide over P and 1 minus P to the other side. So 10 divided by p, which is 0.649, times 1 minus p, or 1 minus 0.649. If I solve for that, what I can find is how big n needs to be. So let's do that. 10 divided by parentheses. I want to make sure that entire thing is down there. So 0.649 times 1 minus 0.649. If I don't have that extra parentheses, it would actually just divide by 0.649. But if I do that appropriately and hit enter, I should get 43.89. So that's how big the sample size needs to be. 43. I'll just say 89, or realistically, n needs to be greater than or equal to 44. So then to answer the question of how many more need to be sampled, that means that we need, in this case, if we already have 30, that means that we need 14 more. Okay. So that can answer that. So if we had 14 locations more, say if we had 45 locations or 50 locations or 60 locations, all those would be okay. But 30 is not good enough yet. It would have been fine if I was dealing with the sampling distribution for a mean, where all I need to check is the central limit theorem, and 30 is perfectly fine. But for this, it may not be good enough depending on what the proportion was. So that's what we needed to check. All right. Now, I'm going to say that on page 7, I recommend trying this on your own, kind of like what we did in chapter 7 and 8. Go ahead and try this one on your own first, and then unpause the video, see how you did. According to a survey in a county, 28% of adults do not own a cell phone. Suppose a simple random sample of 200, that's a lot, adults are obtained. In the sampling distribution of p hat normal and y, so we need to check if it is normal. So we have our two conditions. First, we have np 1 minus p. We want to see if that's greater than or equal to 10. So np 1 minus p greater than or equal to 10. Here our n is 200, which again is a lot. That's usually going to be okay in most cases, but we can check here. 200 times 0.28 times 1 minus 0.28. And what we want to do is confirm if that is greater than or equal to 10. So 200 over here times 0.28 times 1 minus 0.28. Okay, sorry. 200 times 0.28. Whoa, 0.28 times 1 minus 0.28. If I run that, I get 40.32. So 40.32 is greater than or equal to 10. So that's our condition verified. For a second condition, again, this is one that you can argue. Argue, I think, is a little bit easier in this case because we're looking for adults in a county, and we have 200 of them. That's probably less than 5% of adults in that county. Now, again, it does depend on the county you're working with, but if we say something like Salt Lake County or even Summit County, something around here, then we should definitely be able to say that, yes, this is less than 5% of those. However, we can also check that mathematically by doing n, or 200, divided by 0.05. Find what that is, which should be 1,000. Yeah. 200 divided by 0.05 should give you 1,000. Let me just check. 200 divided by 0.05. Oh, no, 400. What am I thinking? Yeah, 4,000. Okay, that's what we check. So 200 divided by 0.05 is 4,000, and we wanted to make sure that that is greater than or equal to capital N. In this case, we could probably say it's okay saying that there's or less than or equal to capital N. We could say that this is probably okay saying that there's likely less than 4,000 adults in that entire county. So this is likely true. saying that this is most likely okay. Or again, we would need more actual demographics, more information to know if that is appropriate for the population, particularly since we don't know what county they're talking about. But anyway, those two confirmed, we should be all right. What is the probability that in a random sample of 200 adults, more than 30% do not own a cell phone? So with that sample size, more than 30% do not own a cell phone. All right, now remember, just seeing that percentage does not mean that we're dealing with an area. That actual 30% is relating to how many own a cell phone. That's going to be a value on my axis. With the values given, we have that the mean is 0.28, so that's what is provided down there. But we also need to know what the standard deviation is. So we have the mean is 0.28. The standard deviation we have yet to calculate. Standard deviation is going to be the square root of 0.28 times 1 minus 0.28 divided by 200. Okay. So we can find that over here. So remember, make sure everything in there is under that square root. So 0.28 times 1 minus 0.28 divided by 200. What we get is 0.0317. If I consider that standard deviation kind of easier, just as like 0.03 just for judgment purposes on my graph, 30% is not quite just one standard deviation away. One standard deviation away would be about 0.3117. But 30% is a little bit closer to that. So 30% or 0.30 is around there. We're trying to find more than that, so we're trying to find the shade region above there. So we can find this using normal CDF. My lower bound is going to be 0.3. My upper bound is going to be infinity. My mean is 0.28, and my standard deviation is 0.0317. With that, we should be able to get an approximate value. So, second verse, hit 2, should plug in our values. 0.3, I already have infinity there for a bunch of 9s. 0.28 and 0.0317. Okay. Plug all that in, we get about 26.4%. Okay. Seems to be okay from the empirical rule. And we can interpret this just like we did in 8.1, trying to relate it to 100 of those samples being taken. 100 samples of 200 adults were obtained. Notice that again we indicate how big that sample size was. That's always important. One would expect about 26 of those samples to result in more than 30% not owning a cell phone. All right. Another one, what is the probability that in a random sample of 200 adults, so still the same sample, that means the mean and standard deviation are consistent, between 25 and 30% do not own a cell phone? Okay. So, between 25 and 30. We know that the middle is 0.28, and we already indicated that if I go one standard deviation away, 30% is not nearly that far. So we know 30% is there. However, 25, that's below 0.28, and the standard deviation is about 3% as well, so it's almost one standard deviation away, just a little bit off of that. So one standard deviation away would be 0.24, 83? 83-ish. And so 25% would be around there. And we're trying to find the area between those two. So then we can run normal CDF on that. The only change here being my lower and upper bound. My lower bound is going to be 0.25, or 25%. followed by 0.30 or 0.3, and then our same mean and standard deviation. 317. Okay. So we can calculate that in our calculator. Make sure we hit second. There's in number 2. We get 0.25 up to 0.3, and our mean and standard deviation are the same from the last question. So we get here a probability of about 56.4, or yeah, 56.40%. So an increase of about 30% from the previous question. Again, we can look at the graph and say, yeah, that makes sense. Both these values are within one standard deviation away. They're not farther than one standard deviation. And I know one standard deviation away is 68%. So this being less than 68% makes sense. Last question here. Would it be unusual for a random sample of 200 adults to result in 50 or fewer who do not own a cell phone, and why? Well, again, this case we don't have a proportion, but we need to check it and make it one. That's 50 out of, in this case, the sample size was 200, not 100. So 50 out of 200, that gives me 0.25. So that's what I'm trying to find, 25% or fewer. On my graph then, we already know that the middle is 0.28, and we already know that 25% is not nearly one standard deviation away. We're trying to find the area there. Now, based on things we know from the empirical rule, we know that this is not going to be unusual. One standard deviation away would have a tail of 16%. This is going to be a little bit more than that. So it's going to be more than 16%, which is more than 5. So it's not going to be unusual. So we should already know that moving into this, but we can confirm with normal CDF. So here, our lower bound is negative infinity, followed by 0.25 as my upper bound. Then a mean of 0.28, standard deviation of 0.0317. All right. So over in our calculator, we can hit second verse 2. And we get negative 999 for my lower bound, followed by 0.25, and the same mean and standard deviation as the previous two questions. We already know this is not going to be that bad. 17.20%. That is greater than 5%, so no. This is not unusual. All right. Hope you did pretty well on those. Hopefully you're getting the hang of it. Last example we'll do here. A researcher is studying the proportion of Americans who are afraid to fly and obtains a random sample of 50 adult Americans and asks them whether or not they are going to be afraid to fly. To say the distribution of sample proportion is approximately normal, how many more adults does the researcher need to sample in the following cases? So, if we have that P, the proportion of adult Americans that are afraid to fly is 20%, or if we have 25%. All right. Well, for A, we need to check to see if n is big enough, and if not, how many more we need. So we can use np1 minus p greater than or equal to 10, and solve for n like we did before, getting n greater than or equal to 10 divided by p times 1 minus p. Or in this case, n greater than or equal to 10 divided by 0.2 times 1 minus 0.2. If I solve for that, n greater than or equal to, on my calculator over here, we can get 10 divided by, again, make sure in parentheses everything on the bottom is down there, 0.2 times 1 minus 0.2. Or you can find what 0.2 times 1 minus 0.2 is separately and then solve from there. That works just fine as well. We get 62.5. Note that n needs to be greater than 62.5, which means that 62 won't cut it. We need at least 63. They have 50, so they need 13 more. All right, so that's A. B is going to follow the same way. Go ahead and try on your own, and then check to see how you did. We can use the same formula here. 10 divided by, in this case, it'll be 0.25 instead of 0.2. So 0.25 times 1 minus 0.25. And then solve for what n is going to result from there. So n greater than equal to, and we'll solve that on our calculator here. So 10 divided by 0.25 times 1 minus 0.25. We get 53.3 repeating. Again, note that n needs to be bigger than that, so 53 won't cut it. That means that they need 4 more, since they have 50 already. All right, so that covers it for Chapter 8. Notice that 8.2 and 8.1 are working with the same situations. We're still working with normal CDF. We're still working with inverse norm if necessary. So all of those are still the same. The only differences are that we are needing to now check to see if they are normally distributed first, and that we may need to adjust the standard deviations. So those are the main differences to take away from this. With that said, go ahead and try the homework for section 8.2. And I hope that this helped. Have a good day.